So it's very nice to be here, and it's a pleasure to be part of the LCA enterprise. I think they're doing an amazing job. So I'm going to talk about climate and the distribution of African ecosystems. Why on earth a talk on climate in concerns about conservation of Africa? Well, everyone should be thinking in their protected area or wherever they're interested in conservation about what is the climate context of where they're working, and, for example, how is climate going to be changing? But there's more than that to this talk. It illustrates, I think, how old ideas can be held long past their useful date, and how we need to confront the realities that we face and shift and change our ways of thinking. So for the last 200 years or so, people have looked at the vegetation of the Earth. Now we can do it from satellites. And they've begun to recognize that there are patterns. There are patterns that in different parts of the world, for example, if you look at South America, Africa, and through to the Pacific, you'll see the tropical rainforests of the world. And they all have very different species, but they share the same basic features of tropical rainforests. So we call these different major vegetation units biomes. They usually cover large areas, they're globally distributed, and they're structurally and functionally similar, usually defined without reference to plant species composition. So there's a definition, because I know the university students here, and definitions are important. When you look at Africa, what you see is that green of the rainforests, and a little bit scattered around there in West Africa. Let me see if I can get a cursor to work. No, I'm not going to risk that. But most of the colors are yellows, browns, or pale greens. And the reason for that is that Africa is full of grass. It's the grassiest biome on the planet. And our little daughter island over there, which is the 4th largest island in the world, Madagascar, is very much like us. The small patches of rainforest, but overwhelmingly grass. It's not just any kind of grass. If you look at this map, the red there shows that Africa is overwhelmingly dominated by C4 grasses. Whereas if you look at Europe, in the northern hemisphere there, it's overwhelmingly dominated by C3 grasses. These are fundamental differences that really, I think, underline the confusion that people from Europe had when they confronted Africa. So what is C4? Well, C3 and C4 refer to the first products of photosynthesis. The 3-carbon sugar is a C3, or a 4-carbon organic acid, C4. C3 is the ancient mechanism. It's where the world started, the ancient plants of the world. And what happens is carbon dioxide, CO2, and water, H2O, is transformed into carbohydrates plus oxygen through the agency of the enzyme rubisco. Rubisco is by far the most important protein on the planet. Must be thousands and thousands of tons of this stuff. And it's a fundamentally dumb enzyme, because it takes CO2 and water, makes a carbohydrate, then having done that, it takes a hard carbohydrate and breaks it down again to CO2 and water, depending on the concentration of carbon dioxide at the site of photosynthesis. So this is not intelligent design. It's a really dumb design, especially when the CO2 in the atmosphere gets very low, as it has been, for example, 20,000 years ago. So what's unique about the C4 plants is that they have a clever way of concentrating CO2 around this enzyme rubisco. So it always works in the right direction, and it always makes a carbohydrate. The old-fashioned plants went backwards and started breaking down the products of photosynthesis. So some of the outcomes of having C4 photosynthesis is that they don't need to open their stomata as wide. So they take up CO2 for much less water loss. So they're very efficient at photosynthesis in terms of water. They can be extraordinarily productive, Sugarcane is a C4 plant. And we've never seen productivity like this from plants. And they use a lot less enzyme, a lot less rubisco to make the tissues. Now, what animals are interested in is the enzyme, the nitrogen that contains it. If they use a lot less enzyme, it means that the tissues have a lot of carbon, inedible stuff, like chewing paper, and not enough nitrogen, not enough protein to keep you good. So they tend to be inedible, and they're also very slow to decompose. So they don't just break down, they sit there staring you in the face for years without decomposing, some of them. C4 plants outperform C3 plants when CO2 is low, as it has been in the glacial times. But it's energetically expensive. So it requires high growing season temperature, meaning that they're tropical, and it requires high light conditions. So they don't occur under forests. They're unique to open areas. So now let's go on to climate and how it influences the distribution of Africa's C4 grassy biomes. And why the obsession with climate anyway, when we look at biogeography? It starts with this man, Alexander von Humboldt. About 200 years ago, he was the first eco-tourist and traveled the world with lots of fancy instruments, measuring a lot of things, including temperature. And he began to realize that places that shared similar climates tended to share similar vegetation. And that observation had led over the next 100 years to a recognition of these major patterns of world ecosystems, summarized by this man, Schimper, in 1903. And he was the first person to put together a recognizable modern system of the major biomes of the world: savannas, deciduous forests, evergreen forests, conifer forests, and so on. And he argued that the reason why the dominant growth forms within biomes changed was because of physiological adaptation. Each environment produced different challenges, and to confront those challenges, plants had different physiologies and different growth forms. So when you went to a particular climate and you saw a biome, what you were seeing there was a physiological optimum for that environment. So this began to get more and more sophisticated, or more and more ludicrous, depending on your perspective. This is a system developed by Holdridge, and it looks incredibly complicated. I don't begin to say that you should try and understand how it works. All it is really is saying, if you know the rainfall and if you know the temperature, then you can predict precisely which biome you have in any given little climate. So each of those little honeycomb cells has its own distinct biome, and a climate uniquely defines that, the contents of that cell. So all the world's biomes have unique climates according to this system. One biome, one vote, so to speak. So what is the honeycomb cell? What is the climate box for Africa's C4 grassy biomes? And then if you were coming out of Europe, what you might expect would be, well, if it's grasslands, they should be in drier places or the tops of mountains, cold climates, because that's where the C3 grasses of Europe are found. Where it's warm enough and wet enough, forests would outcompete grassy biomes. Why? Because plants need light. Taller plants grab the light first, and the smaller plants, the grasses, would be shaded out. So what we might expect in Africa, if you look along a rainfall gradient there from dry to wet, we would expect, and you look at the little line of, those are the grasses there. Don't you like my artwork? No, I'm not very gifted, I admit, in artwork, but it's not bad, eh? At the dry end, it's too dry for grasses, and it's mostly shrubby. As the rainfall increases, the grasses increase, the trees begin to come in, and those are the savannas. And as it gets wetter and wetter, there is a point where the trees form forests and shade out the grasses. So that is now grassland at the dry end, then savannas, then forest, along a rainfall gradient. People realized early on that Africa's grassy biomes burn. They're very flammable. So where would you expect fire? Well, you wouldn't expect it in the dry end because it's not enough grass to burn. As you get wetter and wetter, there would be grass all the time, and you should be getting fires all the time, until you hit the forest where there is no grass to burn, and then the fires would go out. So I got together with colleagues, Caroline Lehman and others, and we tried to ask the question, what are savanna climates? And are there distinct soil types that determine where you find savannas? And do we find the same climates on different continents? And we looked at Australia, Africa, and South America. And we defined savannas as things that had continuous cover of C4 grasses. Non-savannas, forests, didn't have C4 grasses. We used vegetation maps rather than satellite images, because the vegetation maps tell us whether we're dealing with C4 grasses or not. We threw down random points in Africa, Australia, and South America, and we took climate data from global climate and soils databases, and then we ran the standard thing in analysis, multiple regression type analyses, regression trees, lots and lots of fancy statistics that I'm sure many of you are learning about. And what do we find? Well, the savannas are absent where available moisture is high. Savannas are absent where available moisture is low. So not too dry, not too wet, in between, except for Africa, where the savannas occur in much drier regions than they do in Australia and South America. There's another thing about rainfall. Savannas are most extensive where the rainfall is most seasonal. You need at least 5 months of dry season to get. So savannas are predictable from climate. How boring, fits the pattern. Not too dry, not too wet, and the rainfall should be seasonal. And that's what it looks like graphically with the 3 different continents, and the yellow indicates the probability of finding savanna along a rainfall gradient. And that's all very well, but what it doesn't really show is what the other stuff is. And the other stuff is non-savanna. And the non-savanna, even where you have the peak savanna climates, also has forests. That means one climate is not producing one biome, producing 2 biomes. The whole climate zone of savannas is polluted by the presence of non-savannas, of forests. Whoa, yeah, now what's going on? And what we got in Africa is not the pattern I showed you, but this sort of pattern where savannas are widespread, but the forests occur in little blobs like oil and water. They're not mixing right the way across from even dry areas. And as it gets wetter, the proportion of the landscape that is forest increases, but savannas are always lurking there. So these are not a blend of trees. They are distinct units, completely different from each other. And this is a way of representing this. I'm not going to go through it because it's hard to do without a pointer, but go and have a look and you'll see that the tree cover is high in savannas and then declines, and then high in the forests if you focus your eye on the 1800 millimeters at the bottom. This is what it looks like on the ground. There it is in Gabon, Lope Reserve, and there you see the oil and water, the forests and the savannas, quite distinct, not blending at all. The same sort of thing in our own Drakensberg. Same geology, same soil, same climate, but utterly different vegetation, quite distinct from each other. Another example in the hot, dry climate of Shishliu-Umfolozi. So people have been talking a lot about fire, and so we also looked at the probability of savannas, finding savannas and the probability of getting fire. And what this graph shows with the red line is the probability of getting fires. So the probability declines at the high rainfall end where there's no fire, there's no more savanna. That's consistent with the idea that savannas depend on fire. That's what they love. At the low rainfall end, we found the same pattern, that savannas are tightly linked to fire in Australia and South America. But if you look at Africa, there's a huge chunk of savanna which seldom burns. And Africa, we argued, is different because it still has the remnants of the African megafauna, all those animals that eat grasses. So if fire rather than climate is essential for the higher rainfall savannas, then switching off fire should create forests from savannas. And that gives an opportunity for experiment. So of course, we're not the first ones to have recognized the importance, potential importance of fire. And many of the early colonial ecologists and botanists believed that fire was the cause of the savanna. And if you stopped the burns, you would get a forest. And they set up experiments to test this idea in the 1930s onwards. And here's a diagrammatic example from Côte d'Ivoire, the famous Oberval fire plots. And the typical treatments was no burn, keep fires out, late burn, when the grasses are hot and dry. It's the end of the dry season. It's when you start getting lightning to start burning, when the rains are starting to come through, or early burns, which is at the beginning of the dry season, when the grasses are still green. And what you see is a massive impact on trees. And the numbers at the top of that graph there, 27.8, 3, and 15.6, show what's called basal area, which is a proxy for biomass. So what's happened here is with no fire, there are basically 10 times more tree biomass in the absence of burning. And what's happened to this system is it's shifted towards a forest. The early burns, it's 5 times more biomass just by shifting the fire season. So fire is profoundly important in constructing the biomes of Africa. Here's just an example, a local example from Kruger National Park on the left, burnt every year for 50 years, and on the right, where fire's been suppressed for 50 years, and it's turning into a forest. The trouble with these experiments is that you need to run them for at least 30 years. That's a long time. And they're just little pinpricks at a continental scale. What we'd really need to do to see which is climate and which is something else is to have some way of predicting what the climate potential for tree growth could be. And in the 1990s, a new methodology emerged. These are, they're called dynamic global vegetation models, DGVMs, or if they're not global, they're DVMs, just dynamic vegetation models. And what they do is to try and simulate what the vegetation ought to be based on our understanding of plant physiology. So they start with the enzyme kinetics of ribulose bisphosphate carboxylase oxygenase, otherwise known as Ribisco. Whew, years of teaching have got me to be able to say that word without stumbling. They were used for exploring global change impacts. So they incorporated day-to-day climate, and they had to incorporate changing CO2 in the atmosphere. CO2 has more than doubled since the 1800s. So we have a massive impact of CO2 directly on ecological change. They're not very good on soils, but they do incorporate soil depth and soil texture, which modifies the availability of rainfall. And with that information, you grow potential vegetation. You grow the leaves and the branches that support them, the branches that support the trees that make the vegetation. And from that, you produce what could grow in an area. And the critical thing is, unlike our study, you're not using correlations. You're looking for causes. And what you're doing with this stuff is you're testing Schimper's idea that the physiological optimum is what you're seeing in different biomes. Is it correct? We can use these models to see whether what we see is the physiological optimum or something else. So working with Ian Woodward and Guy Midgley, we used Ian's DGVM, the Sheffield DGVM, to test whether South Africa's ecosystems are at equilibrium with climate. And what that simulation does is to show for this part of Southern Africa, the percent cover of broadleaf trees. And you see there are lots of trees with those bright pinks and purples on the eastern side of the country, and it's much drier on the west, which is consistent with the way the basic biomes work. But look at that arrow shows for a specific point in South Africa where we predicted 80 to 90% tree cover. On the right, you see what it really looks like. Whoops! Hey now. That is supposed to be dense, tall forest. It's not. It's not. It's grassland. And what we found is that many of our visitors from the USA or Europe see these grasslands and they say, oh, we went through that dry country where it's all grass. They're completely and absolutely wrong. This is the wettest part of South Africa's summer rainfall area. So we get our water from to run our big cities. So this is very bizarre, very extraordinary. With the model, we were able to introduce a fire module, a simple fire module that produced a fire regimes that were not that different from what we knew was measurable. And that changed everything for South Africa. And suddenly we had grassland everywhere instead of trees. Now, the simulation for that same spot looks much more close to reality. But in the same landscape, you find this. So the climate potential is to make tall forest. The actual vegetation is overwhelmingly grassland. What on earth do you do when you have something like this? So this has also been tested with experiments. And in this case, these grasslands were thought to be the result of frost. But you keep fire out and suddenly forest appears. So it's got nothing to do with frost. Whoops, we got it wrong again. So Old Holdridge got it wrong. There is no unique climate box for Africa's tropical C4 grassy biomes. Those little boxes are occupied by two utterly different biomes, a forest one and a C4 grassy one. And the first person who recognized this was a brilliant American ecologist, Robert Whitaker. He developed a very simple system of relating climate to the biomes. And so if you look at 200 millimeters of rainfall, you'll see, and at 25 degrees, you see you're in tropical seasonal rainforest. If you shift to the left of that, to 100 centimeters of rain, then you're in something which he called, you don't know what you're going to find. It could be grasslands, could be savannas, could be forest, could be shrublands. He gave up. So I call that ecosystems uncertain. It's the climate zone where you don't know what you're going to find. That is a real honesty of Whitaker. Now that looks quite small on this plane of temperature versus rainfall. But when you spread that climate over the planet, goodness gracious me, yeah, it is vast. Huge areas of Africa, in fact, almost identical to savannas, are in this climate zone where ecosystems are uncertain. The fascinating thing for me is look at the Northern Hemisphere. The huge areas of Europe are also in this zone. Well, they all filled up with forest. So there are very peculiar things going on here, which the Europeans need to sort out. They got it all wrong for Africa. We need to get it right for them back in Europe. So be cheeky, guys, be cheeky. If you now look at where that uncertain ecosystem zone is, and then you plot over it the frequency of fire, you'll see it's a very close match for Africa. I'm ignoring the rest of the world, but Africa tells it all. Africa is the area that burns more than anywhere else on the planet. In fact, 70% of the world's annual burnt area is from Africa. Don't worry about it. All the carbon that goes up in the atmosphere after a fire in Africa, those grasses grow so fast that they've absorbed all that CO2 the following year. There's a very fast recycling of carbon dioxide. The problems with burning are in the forests of California, the forests of Australia, the conifer forests that are going up in Greece. When these go up, it takes decades to rebuild that carbon, if it ever is going to happen at all. In Africa, it's a blink and it's replaced again. Now, what's interesting here, I think, from a cultural perspective, from a psychological perspective, fire was considered entirely of human origin by the botanists who came, and biologists, ecologists who came out of Europe. If you look at Europe and you look at the Eastern United States, very influential politically, economically, industrially, these are the places which have the least experience in the world of fire. They have no experience, no cultural experience of wildfire. And their attitudes, naturally enough, are imposed on the rest of the world, and in my view, mistakenly, which is one reason why I thought it's important to give you a sense of climate and ecosystem distribution from an African perspective, and not one superimposed from Europe. So here we are, these wonderful grassy biomes of Africa. And these tropical grassy biomes and C4 grasslands in general are the biggest global anomaly to the climate hypothesis for biome distribution. It's the biggest place on the planet where climate does not predict well the vegetation and the ecosystems that are there. So in our part of the world, in Africa, we need to be aware of this, and we need to be aware of all the repercussions of climate not being a good determinant of what you see on the ground. So how is this anomaly explained? Well, the European experience was, where it's warm and wet, it should be forest, and you only find grasses where it's cold or dry. And that's because they're all C3 grasses, not C4. C4 grasses are extraordinarily flammable. They are lethal things. So from a European perspective, if it's not forest, it must be, and it's grassland, it must be because of deforestation. Axes for cultivation, but in Africa, you see huge areas of grassy biomes which have not been plowed, or by burning. And the belief was that fires are unnatural, caused by humans. What we've realized in the last 20 years or so is that these grassy biomes, these C4 grassy biomes, they're ancient. They're ancient. And when you see a forest and the grasslands, these we're now calling alternative stable states. So savannas and forests, we call alternative biome states. With the same physical starting condition, same climate, same geology, the biological assemblages diverge, become utterly different. And each assemblage is creating the environmental conditions that favor it. So in the savannas, fire and or grazing, I haven't had a chance to talk about grazing because it needs another lecture at least to talk about it. The grasses are highly flammable. They don't decompose, the litter accumulates, they're just crying out to be burnt. In the forests, they shade out the grasses altogether. There's no fuel to burn. And they create a microclimate where fire doesn't work well. They also alter the soil. Forests tend to enrich the surface soils, which helps to promote their own seedlings. Savannas tend to impoverish the soil. C4 grasses don't mind. They can live on very little nitrogen and get away with it. So that also inhibits the colonization by trees. So when in Africa you see a situation like this, the right-hand side there is not because of deforestation. It's an alternative biome state. In this case, it's famos, just after a fire. And the forest on the left is not the only climatically determined system. We have these two completely different systems sharing the same climate, same geology, and everything. But the famos is ancient and the forests are ancient, and they're alternative states. Watch out for them. Neither one is what should be. Both should be. So these mosaics of forests and non-forests are common across Africa. That's Drakensberg up in the left there. On the right is Gabon, and the bottom there is Madagascar. And the differences between these open, sunlit, grassy systems and the closed forest systems are entirely natural. Plants and animals are very different in the two systems. We now realize that they've evolved over millions of years. More and more information is coming in. We would like more and more studies. We'd like to see how birds shift. People tend to work in the one system or the other. We need to have people who work across both systems to understand their interrelationship and how different they are right across Africa. The mosaics are often stable on timescales of decades if you use aerial photographs, of centuries if you use old historical documents, or if you go through paleoecological tools, thousands of years. So a grassland that lives for thousands of years is why we call it a stable state. We decided we needed to have a special word for him, and Joe Feltman used a term that the Americans like, old growth. They talk about old growth forests. We're now talking about old growth grasslands, and they're rich in plant species, and they have different kinds of plants, particularly plants with large underground storage organs that laugh at fire, and they just bounce back when fires go through them. Very different from secondary grasslands, the true products of deforestation, which have low plant diversity and also low functional diversity. They lose the plants with those underground storage organs. So they're actually very distinct in places where we've looked at it, and we've looked at them here in South Africa, but we need a lot more knowledge. We're still ignorant. So to summarize, Africa is a grassy continent. Celebrate it. The grasses are C4. Celebrate it. They're different from Eurasian grasses. The Eurasian grasses are very interesting, and we need to understand them better. And now we're seeing signs that they are trying to study them more. Africa's grassy biomes support the largest remaining megafauna on the planet. They support the most frequent fires. 70% of the world's burnt area. Celebrate that. Don't bemoan it or write long letters complaining about it. It's natural. It's part of what we are. Africa has the longest history of humans and our ancestors. So humans are very much part of our nature. And the biota of Africa, the plants and animals, are not leftovers from forests that's been deforested. They're ancient, they're diverse, they're specific to these open grassy systems. What do you think this means for conservation? What do you think? I was going to give you a minute, but I've probably already gone over my time. But think about it. What do you think it means for conservation? I've got a very short list. I think it means to give due credit to forests and savannas. Very often the forests get all the attention. The savannas are also rich and diverse. We need them both. Look after them both. Another critical thing is savannas require active management. A fire policy is necessary. If you decide you don't want any fire, that is a major management decision. Your savannas will change as a result. If you decide to burn, the savannas will change as a result. It requires active management, just like the herbivores. What species mix? Should I bring in rhino? Should I bring an elephant? Oh, what a nightmare. That'll make a big difference to the ecology and the shape of the ecosystems within your protected area. So unlike, say, a beech forest in Germany, where a protected area is one where all you need to do is to stop people chopping down trees, in Africa, you have to go in and manage grassy systems. Climate change is complicated, because climate is not directly linked to those biomes. But what we can do is potentially shift the direction to the places we want by manipulating fire and herbivores. The last point is beware policies emerging from Europe, especially, and the Eastern United States, especially, to go and reforest Africa's disastrous deforested areas. When they see our grasslands, they think it's been deforestation. But for Africa's grassy biomes, there are areas that are deforested, and target those for reforestation. But be aware that you could be targeting an ancient old growth grassland and putting trees in it, which would be a disaster. The trees that you plant are often invasive, and when they spread, they're going to eliminate Africa's native biodiversity. And that's it. Thank you very much.
So lovely. In true millennial fashion, we have all the questions here that you posted in the chat section, and please carry on doing that. We'll try and have Professor Bond answer as many as he can. The very first one from Brad Nelson. What is Professor Bond's opinion about the Great Green Wall project? Professor?
Look, I might end up in trouble for this, but I think it's nonsense. Sorry about that. It's been tried before, and it's failed. And there are places where the trees will survive, and there are large places where they will not survive. So even the existence of the green wall is threatened. It's certainly not going to go right across Africa. And there's good studies already showing it. If the trees do manage to take hold, they like to dry out the water table and make things very difficult for the people. However, I have seen a spin-off of the Green Wall project with somebody planting baobabs, and recognizing that there's a potential small industry there of harvesting the fruits of baobabs. So if that's going to happen, then I'm all for it. But the idea it's going to stop the Sahara spreading, it's a fantasy. And I know it's a fantasy still very popular, but show me the evidence.
Thank you, Professor. Thank you, Brad, for that question. The next question in chat section is from Brilliant Falane. Can climate change be responsible for the changes occurring in grassland biome in the Midlands? Encroachment by Bachiella siberiana, who possesses nitrogen-fixing bacteria, as they are slowly changing into open woodlands.
No, I'm afraid this, I think, is a major threat to the future of grassy biome, certainly in southern Africa, and I think it's also a problem in other parts of Africa where the trees are thickening up, and there is a threat that the savannas will be lost and shaded out. In my view, the main thing that's changed is CO2 concentrations. And with higher and higher CO2, the balance has been tipped in favor of trees, and the grasses that used to thrive under low CO2 are now not doing nearly as well. So I think we've got a real problem. And in my moments of extreme doubt at 4 o'clock in the morning, I wake up weeping for the future of savannas. Yeah.
Thank you very much, Professor. Brilliant. Thank you for your question. All tried and trusted Marty. Thank you for your question. From Marty Jasper. Thank you, Professor Bond. Is it not exactly that? It's a balance of fire, biota, and humans which preserve the habitat. There's 2 question marks.
Well, we know that savannas did fine and existed in Australia and South America where there were no people. So they don't require people to maintain them. So historically, before people got to South America, there were savannas there. And they've been there for millions of years, long before any humans arrived. So they can get along just fine without humans. But what's more challenging is to try and work out how extensive were they in Africa, and to what extent have people made a difference. And that's a really challenging thing to do. Sally Archibald and her colleagues have tried to, from WITS, have tried to look at that. And they reckon that the first impact of humans was to reduce fire by husbanding livestock, and that by concentrating on livestock, they ate the grasses and created fire breaks. So how about that? That's a bit of a surprise. But I would welcome, some bright sparks out there. If you've got a good idea of how to go about understanding the human impact, it's one of the biggest mysteries in the ecology of savannas, the ecology of grasslands worldwide. So think about it, and you could make your name if you found an answer.
Wonderful. So for all those bright sparks, joining us from the universities, there you go. Your PhD thesis is there. Now, the next question, I'm going to have to turn my screen because Dr. Paul Telfer, if I'm not mistaken, he's in Sudan at the moment, wrote a thesis. So there's a statement and then the question follows. Paul, thank you very much. Interestingly, Professor Bond mentioned Gabon, which is generally considered a country that sequesters more carbon through its forest than it produces. He also mentioned that grass fire CO2 emissions are offset by regrowth within a year, which means that fires in the savannas don't significantly contribute to greenhouse gas accumulation. The question, if fires are reduced, is there a net carbon sequestration over years, and how does that compare to forests? Or is there a way we can help protect these grassland savannas to help the climate changes, I think? Yeah.
No, I mean, those are good questions. And the short answer is we don't know. But what people are arguing is that the trouble with planting trees is that they can burn down. Grasslands burn all the time, and their carbon is stored below ground. So there's a lot of carbon in the soil organic matter in grasslands. It's basically protected from fire, protected from drought, and protected from mammal herbivory. So people are suggesting that for stability of carbon, the grasslands could be better than forests. I just put that out there. I'm not necessarily subscribing to it. I think we also need to know more about how different forms of management of grasses influences how much carbon they do sequester.
Wonderful. Thank you very much, Professor. And thank you, Paul, for that, that incredible question. And then from Quinton, here in Limpopo, we have lost our grasslands to forestry. And now the forestry is being replaced by avocados. Any feeling about avocados, Professor?
Well, how sad, eh? But I do have vendor friends, and I know how much they love avocado. So, we need to use land for crops. We need to use land for forestry. South Africa had very little forest. The point is we need to use it wisely, and using it for carbon sequestration when, because of the idea that grasslands are somehow the product of deforestation, is just muddled thinking. It's a disastrous idea. And that should not be part of the equation when we think about how we should develop our land use in the future. We need agriculture, we need forestry, but we need to do it for the right reasons. And we need to preferably make darn sure that when we're doing those land conversions, we're not destroying some of our best and most precious grassy ecosystems.
Wonderful. Thank you, Professor. So next time when you have your avo on toast, make sure you listen to this. From Guy Midgley, is the risk of afforestation to biodiversity in Africa finally being recognized internationally?
Hello, Guy. Well, after we wrote that paper, it's made a difference. And I believe that it's not just us. There is now growing recognition that tree planting has lots of problems attached to it. I have to say that the people who initiated these massive tree planting projects have said nothing about whether they're going to reduce them, including the IUCN, sadly. International Union of Conservation of Nature was behind the bond challenge. And despite questions about its impact on nature, and despite concerns about plantation trees, which could then become invasive, as they have done in many parts of the world, including our part of the world, IUCN is mute about revising or changing the bond challenge. So yes, I think the anti-tree planting lobby is growing, and there's a greater appreciation for, if you are going to plant trees, do plant them in the right place with the right trees and for the right reasons. And that's good. So I'm quite optimistic about it.
Wonderful, thank you. And another question from Guy. Are Californian politicians crazy for thinking that, quote, forest undergrowth clearing, unquote, can reduce fire risk in their ecosystems?
Yes, they're crazy. And I base that on trips to California with my friend and colleague, John Keeley, who's an expert fire ecologist in California. And he just shakes his head in sorrow. You know, it can help to inhibit the fire spread at the very beginnings of a fire. But otherwise, it's just a futile job creation exercise.
So any Californians listening, if you are policymakers, you know. Andy Klee, all the way from Devon in the United Kingdom. Any policy advice for us here in Western Europe?
Well, I've been very concerned recently, just before lockdown. I had the pleasure of visiting Scotland, and I was very disturbed to see the extent of tree planting there in the highlands, these magnificent open ecosystems, which are now being planted up for pine trees, again, because of this fallacy that the highlands were once covered with forests, whereas the paleoecological evidence is showing that they were amongst the most open habitats of Europe for thousands of years. So I would be just watch out and celebrate the open systems that you do have. The downs are magnificent. Who would want to go and plant up the downs to trees and destroy those grasslands? And I feel the same about Scotland. So I think, within Europe and within Britain, you need to celebrate what they call semi-natural grasslands or semi-natural open shrublands. They contain their own diversity, and they contain their own sense of place. When it comes to the rest of the world, start finding out about how we're beginning to understand at last our systems after shedding 200 years of the wrong idea.
Brilliant. Thank you very much, Professor. And thank you, Andy, for that question. I'm going to have to turn my screen again. Emma Ferreira from the University of the Free State, let's just make sure that I can do what I want to do, has written an impressive piece. It does not want to work. Good evening. I have two questions for Professor Bond. Firstly, based off of your research, what suggestions do you have for the youth in moving forward in the fight against climate change? And then secondly, increasingly more emphasis is being placed on biodiversity loss in a world where vegetation is constantly is in a constantly dynamic state, how can we push for biodiversity conservation of an area where species composition is constantly changing throughout the timeline of the life of the Earth? Thank you.
Well, when you get the answer, please tell me. No, I do get asked the question about the savannas. Look, if the trees are coming in because of CO2, and we're going to lose all the savannas, should we be fighting it? Should we just let them go? And I would say we should fight it as long as we possibly can. We shouldn't just allow the carpet of biodiversity to sweep away underneath our feet. We should do the most that we can to keep it there and to preserve those things that we love. For the youth and how to confront the future, I think you need to be curious and without being disrespectful, be cheeky, question things. Here's this professor from UCT, blah-de-blah, fellow Royal Society and so on. You're very welcome to say, it's all a lot of nonsense. And then it's my responsibility to fight back again. So you must be cheeky about what people are suggesting should be your futures.